Last week we introduced the main formalism that we are going to use in this course to describe many-body systems of many particles. And this is the second quantization formalism. And I want to first remind you of the main building blocks of this formulation. And we'll see how we're going to use it for specific purposes. So first of all, how do we describe a quantum system of many particles? The first stage is to identify a set of quantum numbers so these are quantum numbers or quantum indices of single particle states. So this is something that you know how to do from the quantum mechanics of undergraduate, right? For example, lambda can be the position, the coordinate, it can be a momentum, it can include a spin, we'll see examples, anything, but it's a set of, a full set of quantum numbers in terms of which you can describe the Hilbert space of a single particle. Okay?
What is hashtag means?
Number. You're not familiar with this notation? Okay. Okay, so yeah, I know that hashtag for you means something else. I'm a boomer. Okay. Okay, so the next thing is, so we know the quantum numbers, and we can choose them arbitrarily. Today we'll see how to also switch from one base of quantum numbers to another. The second thing is we have to define a vacuum state. What does it mean, a vacuum state? Now, this vacuum doesn't have to be empty in the simple sense. We'll see an example where it's convenient to choose it to be some reference state that is actually not empty, okay, for certain purposes. But how is it defined? It's defined in such a way that if we now define, and perhaps this should have been the line before, we define A lambda and A lambda dagger to be the creation and annihilation operators of particles with a quantum number lambda. Then the vacuum state is defined in such a way that all the A lambdas acting on it give 0. Okay, that's a definition of a vacuum. Okay, so if this is true for all lambda in my basis, then this is a vacuum. Okay. So, and A dagger creates a single particle, and if we want to create more than one particle in the same state, in the same single particle state, then we can apply it as many times as we like. And then for these operators, A and A dagger, we define there are operators that their meaning is creation and annihilation of particles. They have to obey a set of commutators or anti-commutators, depending on the statistics. And let me summarize them. So they have to obey that for any A lambda prime lambda dagger A lambda prime. This is 0, and A lambda prime dagger is a delta of lambda prime. And what I wrote here in terms of standard commutators, this is for bosons. For fermions, I get exactly the same in terms of anti-commutators. And okay, I'm not reminding you remember what they are. It's AB minus BA or AB plus BA. So the difference between fermions and bosons is that the commutators are replaced by anti-commutators. Okay. So if I have a many-body system with a set of identical particles, of course these relations only are true for identical particles. If they're all electrons or they're all photons, okay. And so one piece of information that I have to know when I'm describing such a system is what is the statistics, fermions or bosons. Okay. In more fancy cases, we can define something in between, but we will not do it in this course. Okay. And with this set of basic algebra rules, of course, we can calculate commutators of any combinations of A and A dagger, okay? And you're going to use it a lot. In particular, for any type of quantum particles, with the set of A's and A daggers, we can define a number operator, or actually let me write it with a small n, just for, let's define it with a small n. This combination, A dagger A, is playing the role of a number operator. How do I know it? Because if I define a state, okay, maybe we'll I'll write it next. Okay, so here I define the set of operators in an algebra, and from this you can get everything. Every operator that you can express as some combination of A's and A daggers, you know how to work with, and you can calculate its matrix elements and expectation values using this language. Okay? So now we come for the states. All the wave functions describing many-body, Hawk states. All the many-body wave functions in our system are going to be described as superpositions of basis states that belong to the Hilbert space called Fock space. And in this state, it's a set of states that look like, let me now write it with the lambdas, n lambda 1, n lambda 2, okay? So this kind of states are for any choice of n lambda and any choice of terms in this expansion. These are the bases, okay? They're states with well-defined number of particles, and for each of them have different occupations for different quantum numbers. Now we can write these states in terms of creation operators. So let me do it Okay, so how shall we write it? And I'm now writing a compact expression. So such a state can be expressed as, and they are also defined such that they are normalized, and of course they are orthonormal. If not all the ends are the same, if you take an overlap or between this state and something with n prime, only if all the ends are the same, you get 1, and otherwise 0. Okay, so then it's an orthonormal basis. Now let me write how it looks in terms of creation operators. So it's a product of all the lambdas in this series there's a normalization factor of n lambda factorial a lambda dagger to the power n lambda acting on the vacuum. In other words, each Fock state is a simple product of a harmonic oscillator-like states. They are not really harmonic oscillator because this is also true for fermions, where we apply the A dagger n times to create n lambda particles, and it's a simple product, right? Because each quantum number are independent. Okay, and this is it. This is the wave function, and then you can see that if I want to calculate a matrix element of some operator that, like for example, the number operator or the total number operator, how shall I write it? By the way,
ni.
Exactly. So it's a sum over all lambda of n lambda of n lambda, right? Very simple. So if you calculate the expectation value of this operator, the calculation can be done relatively simply using this expression and the algebra. And you will, in your homework, next homework, I think, you're going to prove some identities, some algebraic identities that will help in such calculations. Okay? Okay, so that's the formalism. And the next thing I want to show is, suppose now I have some basis of states, but for some reason I want to add a term to my Hamiltonian, and I see that the old basis is not good. I want to change to a new set of quantum numbers. How do I do this change of basis? And you know that as in standard single particle quantum mechanics, we can always switch from the momentum space to real space, for example, right? This transformation, which is a unitary transformation, does not change our result. It's only, we are allowed to do it as long as we keep track of the transformation of everything. In the end, if we calculate some physical quantity, the result will not depend on the basis, and you can choose it just for convenience. Okay, so this is what I want to do next. Let me leave this part on for the time being. Change of basis. Okay, so suppose I have some set of quantum numbers I denote by lambda, and I want to switch to a new basis, which I call, okay, maybe not lambda prime, let me call it eta. Okay? It's a different set of quantum numbers. Okay, and I know that in each of the bases I'm allowed to define my creation and annihilation operators, and I can actually relate them to single particle wave functions, because what is the state lambda? Okay, if I'm writing the state lambda, a single particle state with quantum number lambda, how will it look like in second quantization? It's only one particle at the state lambda. What? Right, so actually I can write it as just applying a dagger lambda once on the vacuum. Okay? So this is an identity. Okay? Now, in first quantization, if you like, this is a transformation between second quantization to, or first quantization to second quantization for one particle. In first quantization, we know how to change basis. I can write the same thing for the other quantum number, right? So I can define, and if you like, I can use it as a definition for A eta dagger, which is something that if I apply on the vacuum, will create a state. Yeah?
Why you need to change basis? I don't understand.
In some cases, you need to change basis. And we'll see examples. Okay? For example, you have a problem that was defined in real space, and you see that going to momentum space is nicer. Okay? We're actually already seen such an example. Okay? But then you have to know how to do it in general. Okay? So, okay, so now I want to find a transformation that relates a lambda dagger to a. How do I do it? First of all, let me express the state eta in terms of an expansion in the basis lambda. And we know how to do it because what you need to do is to use resolution of identity, right? This is what I wrote here. You're familiar with this, right? This is just the identity operator. If I sum over all lambda prime, and I have to apply this on the on eta. Sorry, yes, on eta. Thank you. Okay. Okay. Let me see. Is that what I wanted to do? Yeah, okay, that's fine. Sorry, yeah. Got confused for a minute. So let me erase the prime because it's just confusing, okay? This is just a dummy index, okay? All right, now this is a number, right? Which is basically the unitary transform. It's a matrix element of the unitary transformation from the basis lambda to the basis eta. But because it's a number, I can move it here and rewrite it as a sum over lambda of lambda eta times lambda. But what is lambda? Lambda is a dagger lambda acting on the vacuum. So I find that eta can be written as a sum over lambda, lambda eta, a lambda dagger acting on the vacuum. But on the other hand, the left-hand side of this equation can be expressed in terms of a eta acting on the vacuum. So basically, what did I get here? I get that a dagger eta is actually identical to this thing, right? And this is an identity between operators because I define these operators according to how they act on the vacuum. So, so then we don't need to write the vacuum, and let's write the final result. So I can erase this, right?
No.
No? Okay, so I'll make some space. Okay, so what did we just prove? It's very simple, that a eta dagger is actually a lambda, lambda eta times a lambda, okay? And this, if you like, you can define it as the lambda eta matrix element of a unitary transformation, but it's just a name, okay? That is a changing basis in the single particle state. And yeah, and this is what we need. Let us take an example. Yes? Because this is a definition, in a sense, this is a definition of the A dagger. Of course, if this is true, one can show that it's, I mean, we define the A dagger in a more general way, but basically it's right, yeah, I mean, you can do this for any state, but this is just a simple, and in fact it's enough, okay? Okay, so let's take an example. You asked why is it good for? So I want to go back exactly to this example. Suppose I have particles that I define the creation and annihilation operators in real space. And then I have a set of operators that okay, maybe we'll do it in general, not necessarily in one dimension, so I want to write it like this. So the coordinate R is an example for a quantum number. It's actually a continuum of quantum numbers. And I can define the following operators. Now notice that I don't denote them by A, but rather by psi, but don't confuse. This is not a wave function. Get used to it. Why I'm writing it as psi and psi dagger? Because in the literature, most of the literature, for the specific case of real space operators, you denote them by psi, okay? But they have exactly the same meaning as the creation and annihilation that we are familiar with. But notice that they are in a continuum. So what does psi dagger mean? If you apply it on the vacuum, you create a particle at exactly a point R. Now notice, because R is a continuous variable, we have to be a little careful. So these psi and psi dagger, and that's also why you denote them with a different letter. They have dimensions. They have dimensions because if you create a particle at a point, and it's within a continuum, actually it doesn't have much meaning unless you allow for some small environment around it, infinitesimal environment. Otherwise, as you know from also from undergraduate quantum mechanics, the probability to find the particle exactly at the point is actually zero. Okay? Only if you can only talk about probability density. For that reason, I have also to modify the definition of the commutators for this. So if I look at the commutator or anti-commutator of psi of R and psi dagger of R prime, what is it for bosons? Okay, or actually let me write
Delta
It's that, exactly, right. So the delta of the chronicle delta will become delta of Dirac. And this will have units of density, 1 over volume, and that's why the operator, let me define now, an operator rho of R to be psi dagger R psi R. What is the meaning, physical significance of this operator? Why did I denote it with a rho? Exactly. Yeah, it's the particle density, not particle number, it's particle density. So this is the density operator. And it's a very, very important operator because when we get to talk about the interactions between particles, the density of particles comes in the expression directly. Okay? Okay, so good. So so this is a definition for creation and annihilation. Yeah?
It's delta R minus R or
R prime. Sorry. Yeah. Sorry. Thanks. Typo. Okay? Of course. Yeah. Okay, so so now I suppose I write some expression in terms of psi's and psi dagger, but I see that it's very inconvenient. You get derivatives, for example, and things like that. What do? You say, okay, I want to change basis. And it's possible that the convenient basis is momentum space. So we want to change from psi of R psi dagger to AK and AK dagger that are creating and annihilating particles at momentum state or wave vector state K. Okay? So how do I relate them? This is the transformation. Of course, I forgot to mention something. So what I wrote here is a transformation for the A daggers. What if I want to change, what will be the transformation of A? I don't have to recalculate it from the beginning. I just take the conjugate, Hermitian conjugate of both sides, right? So let's write it explicitly. So I have another equation, if you like, for A eta. The annihilation will be a sum over lambda. Now, because I put a conjugate here, and this is a complex number, I have to exchange exactly. So it's eta lambda, or if you like, it's lambda eta star. Okay. So this is star times a lambda. Okay. Okay. So this is simply the conjugate of this equation. All right. So let's apply it for our case. So psi dagger r is going to be a sum over k states, and let us assume that we have a discrete some boundary conditions, and we have a discrete set of k's. Otherwise, we go to the integral, the usual thing. But just keeping track of a discrete space, we sum over k, and now I'm applying this formula where the lambda is now going to be k. Okay? So here I put, let me first write it explicitly. Okay, it's the overlap of r and k. Okay, and we'll write it more nicely in a minute. A dagger k. But what is this? Or maybe let us look at, let me write the other transformation for the annihilation, where here I have the overlap of k and r, ak. Okay. What is this? Another way to write it. The single particle state with well-defined momentum, it's a free particle state. And the overlap with R is the real space representation of the wave function of a particle with momentum k, of a free particle with momentum k. What is this wave function? Remember? What? No, it's a state, it's the state k, okay? The state k, if I represent it in real space, this is phi, let me write it differently, it's phi k of r. This is now it's a wave function, okay? But what is the wave function of a free particle with wave vector k? It's there is some normalization factor times e to the I k dot r, right? This is what it is, and if I plug it into this this formula, I get so let me plug it in. I get, there's some normalization factor, omega here is the volume, times sum over k of e to the I k dot r a k. Okay? So this is the transformation of the annihilation operator, and what have I got? What is this? Basically, it's a Fourier transform. Okay. So the AKs and the AK daggers are Fourier components of the real space field operator, psi and psi dagger. Okay.
What omega mean?
Omega is a volume. Okay. In this course, different. In this course, omega is volume. If you have to keep track of size of the system. Okay. Okay. Very good. By the way, from this you can see explicitly that psi has dimensions of 1 over square root of the volume, because everything else is a pure number in terms of units. All right. Very good. So with that in mind, let us now define. So we defined our wave functions, the basis for all our many-body states. We defined algebra for the creation and negation. We know we have a prescription how to change basis if we like. And the next thing we want to do is to be able to express every operator that describes a physical quantity in terms of these building blocks. Okay? Okay. So let me do it. So the first type of operators, I'm going now to classify my operators a little differently than what you were used to. So in single particle quantum mechanics, you define operators like coordinate, momentum, kinetic energy, potential energy, you know, things like that. In a many-body system, we have to think of various kinds of operators according to how many particles they involve, because there are operators that act only on one particle. Okay, for example, we'll see examples, but this kind of operators we call a one-body operator. But we can define a two-body, a three-body, a seven-body. What does it mean? It's classification according to how many particles participate in the operator. Okay? For example, the interaction between, like Coulomb interaction between two charged particles.
Two-body.
It's a two-body operator, exactly. But we can, usually in most cases, we are mostly interested in either one body or two body. This is already complicated enough in the general case. But in some cases, you can have interactions of three particles simultaneously. And you can have more complicated things, but in terms of just how to write them down, there's a very simple prescription. You can almost guess it, but let me derive it systematically. So first let us look at one body operators. And the definition is, let me denote it by O1. One is for one body. It's something that you can write in the form of, let me first write it in first quantization. So suppose I have n particles. I is the particle index. Okay, this is the particle index. And OI is an operator that acts on only one particle, on particle I. For example, let us take a simple example, the kinetic energy of a set of n particles. How shall we write it? Let me denote it by T. How can we write it in first quantization?
C בריבוע. C נגזרת בריבוע חלקי.
למה C? P בריבוע חלקי. Right, so it's okay? This is it, okay? Simply the sum of single particle operators. Okay, so and there are many such examples. Now we can always find for any operator we can find a basis that diagonalizes it, right? So let us now let us choose such basis. I will call it lambda. Yeah?
I not understand. What is O1?
O1 is a single particle, is an operator that acts only on particle I. I here, the index I is a particle index. They are, of course, identical particles. So if I really look at the many-body system of identical particles, I cannot distinguish them. It's not a useful index. That's why we're going to replace it by something else, which is the quantum states, the quantum numbers. But this is what it means. For example, pi squared over 2m is the kinetic energy of particle I. All right?
Mm-hmm.
Okay. Now, I can define a basis, lambda, to be the basis of eigenstates of OI. Okay, so OI is a single particle operator. This is a little o. Okay, maybe I'll make here, I don't know, a notation. This is a little o and this is capital O. Okay? Little o is for single particle. So O acting on lambda is O lambda times lambda. Okay? Now notice that here I don't put an index of a particle because I don't care about the index. Okay? It's an operator. In this representation, it's an operator that acts on a single particle. I don't care which particle in this. By writing this, I assume that I can distinguish the particle, but I don't. Okay? So, for example, the kinetic energy is minus h bar square, Laplacian of over 2m, right? Okay. Right, so, but what is lambda here? What is this? It's not necessarily, now we are completely general. Okay? Forget that this was just an example, okay? Now I'm being very general. And I know that lambda here can be expressed in second quantization as a lambda dagger acting on the vacuum. And I want to be able to represent O, little o, in such a way that when I act on this, I want to represent it in terms of A's and A dagger of lambda, so that it will give me this eigenvalue equation correctly. Okay? How do I do it? So I'm claiming that, let me now write a definition. Okay? If I write it, in such a way okay, maybe I'll explicitly use the definition we had for the number operator n lambda. Okay, and I remind you that n lambda is a lambda dagger a lambda. Then if I define O, little o in such a way where O lambda here is the eigenvalue, okay? If I apply it on the state, let's just apply it on the state a lambda dagger 0 and see that it works. Now I have to be a little careful because if I express O in terms of the sum, I have to have a different index. Let's call it lambda prime. Okay? So it's a sum over lambda prime of O lambda prime n lambda prime acting on a lambda dagger acting on the vacuum. Okay, and this is a sum of terms. Now let's write it explicitly. Because n operator is a lambda prime dagger a lambda prime acting on a lambda dagger. All right. Okay. Now I want to do the following. Notice that here I have an annihilation operator, right? And I can use the commutation relations or the anti-commutators to replace it by, let me write it down. I'm just reminding that a lambda prime dagger zeta, okay, is delta of lambda prime. I'm deliberately writing it like this because it's either commutator or yeah.
Can you repeat why O small o is equal to sum of this?
Why is this?
Yeah.
I'm now proving it.
Oh, okay.
Okay, because I know that it has to obey that if I apply it on lambda,
Yes.
I just get O lambda. Okay? Okay, so if you like, this is now a question mark, and we're going to prove it. Sorry, yeah. Okay, so I'm now going to use the algebra.
בעצם נעזרת כרגע במשהו שצריך להוכיח בהמשך כדי להוכיח פה משהו נוסף, נכון?
I'm actually claiming that this is a representation of O,
כן.
okay? And I'm going to prove it. Yes.
אבל קודם כל משתמשת בזה כאן בשביל להוכיח משהו אחר.
No, so the way, okay, I'm saying the following. Okay, let me guess, I'm guessing the representation. I take it and apply it on a state.
והתוצאות שזה צריך לסיים.
And then I'm going to prove that it's going to be an eigenstate. Okay?
זאת אומרת, רוצה להוכיח שזה יהיה ממש מסוכנת.
Yes, I want to show that the result of this operation will give me back what I know is true. Okay? Okay? All right. So what am I doing? I'm taking this commutator or anti-commutator, and from this I can rewrite it as follows. And the product of a lambda prime dagger you can change, you can switch the second expression to the other side and write it as delta lambda lambda prime minus zeta of a dagger lambda prime a lambda, right? This is just using the definition of the commutator. Okay, where zeta for bosons, it's going to be, sorry, that's plus. It's plus, sorry, right? It's plus because for bosons it's plus, and for fermions it's minus, right? It's an exchange. Okay, but notice that if I'm here writing, I'm replacing it by delta lambda lambda prime plus zeta a lambda dagger a lambda prime. No matter what is zeta,
No.
what will the second term give?
You need to change the
אפס.
לא,
זה אפס מכיוון שזה פשוט.
להפסיק, no?
Exactly, right? After, so I'm replacing this by a sum of two terms, delta plus this. But the second term will give me zero because I get annihilation acting on the vacuum. Okay, very good. So therefore, I throw it out and I see that it's given by sum over lambda prime O lambda prime a lambda prime dagger times a delta and all that acting on the vacuum. Okay? And because of this delta, the only term that survives in the sum is lambda prime equal lambda, right? So, therefore, I see that I have to copy it here. Okay. So what did I show? That if I take this definition for O and apply it on a lambda acting on the vacuum, what I get is O lambda, I'm now applying the delta, O lambda, a lambda dagger acting on the vacuum. What did I get? That this representation applied on one state, on the state lambda, this is just the state lambda. This state is an eigenstate of O, the way I defined it, with an eigenvalue O lambda. So, in other words, this equation is the same as this. Okay? So, I see that this is how it works if I apply it on a single particle, and therefore I can now go ahead and see what it does if I apply it on a state with many particles. Okay? Now for that, so we're not going to play this game with using the commutator and exchange every time we have a long string of operators. Let us use here an identity which you're going to prove in your homework, I think, or in one of the exercises. And it's the following actually, I think it's almost trivial. So if you take this operator and apply it on a lambda dagger to the power n lambda acting on the vacuum, what is this state? Up to normalization, of course. if I add the 1 over square root of factorial, etc. This is just a state with n lambda particles, okay? With n lambda particles at state lambda. That's what it is. So this operator acting on this will give you the number, okay? N lambda without a hat is just the number of particles, which is the number of times we applied this creation operator. Okay? So all the states with well-defined number of particles at a given quantum number are eigenstates of the number operator with eigenvalue and lambda.
רגע, אז פה אנחנו חושבים שזה למצב מאוד מאוד בסיסי למעלה, נכון?
Right. This is for single particle state, but it's also true for arbitrary.
רגע, אז איך הרחבנו את זה כשתתחלנו להפעיל את האופרטור הזה יותר פעמים?
Yes, you will prove it. Okay? And you'll use some algebra rules. Let's not get into it. Okay? I'm just using the result. Okay? And it's very easy to prove. Okay? And if because this is true, then I actually see that if I take this operator and apply it, so let me now write down the following expression for a single body, a general single body operator. With this. And just as before, let me put here a question mark, but we're going to very soon see that it works. I'm claiming that the sum over all lambda, let me write here all, because sometimes you can have a partial sum. Here we sum over all the bases of single particle states lambda, O lambda, A lambda dagger, A lambda, or if you like, I can directly write it as the number operator N lambda. Okay? And now I take this operator and apply it on an arbitrary Fock state. Okay? And once I know how it acts on a Fock state, I know what it does for any state, because any state is a superposition of such things. And I can also calculate matrix elements by taking the overlap. So let me see what happens if I apply it on a state with just an arbitrary state. Okay? Okay? Now what is this state? As we've seen in the beginning of the lecture, it's something that you can write as a product, I'm just reminding, M2. This can be written as a product of all, let me call it lambda prime of normalized states, A dagger to the power N lambda prime acting on the vacuum. It's just a product of states with N lambda at each lambda. When I apply it on such a state, what will I get? First, let me write it explicitly. There's a sum over lambda of O lambda, and now I have to apply the number operator N lambda on the state. Okay, what will I get from application of this is just a number, and I'm applying it on a state which is a product of states with some number at each lambda. What will be the result? So, first of all, when you see that when I take it and apply on such a state, all the lambdas here that are different from this particular lambda will do nothing, right? It's just yeah, it's not doing anything. They are eigenstates with eigenvalue 1, but when it acts on the particular lambda, it will give me the eigenvalue n lambda times the state. Okay? So if you like, I can take the operator and when it acts on such a product of many states, I can just bring it over to the appropriate lambda, and I see that I just get a number times the same thing. Okay? And therefore, yes, let me do it more explicitly. So I can write n lambda operator acting on a product. Let me write the product explicitly. It's like lambda 1 to n lambda 1 times, okay, it's a long string, and then somewhere inside I have a dagger lambda to the power n lambda of the same lambda. Okay? Now all the others, these are all different from lambda. I can take it because it commutes with all of them, right? It commutes with them. I can bring it over here, okay? And it will just give me, and it will just act on this and give you a number. Okay? That's all. So therefore, what I'm getting is, let me erase it just to make it.
Yes,
Okay, sorry.
You can erase.
Okay.
אבל זה לא אמור לסבר הפוך שה-A למדה אמור לפני הפלוס ואז...
No. Why? No, the operator acts on everything else is on the right.
ואז כאילו מוזז את...
I move it, I shift it through all the indifferent things until I get to the point where it does something.
כן, ואז זה לא יהיה אופרטור מספר, אבל זה יהיה משהו.
Yeah. Okay, so, and then it gives me, so this will give me, so it will give me just n lambda times what? The same thing, because it's an eigenvector. Okay? And now what did I get? So for each lambda, I get the same state multiplied by the number n lambda times O lambda, right? And I do it for every lambda. It's a simple sum. And therefore, what will be the result? And all the terms in this sum will give me some number times the state, the same state. So the whole state is an eigenstate of the one-body operator, the way I expressed it. And it gives me, let's see what it gives. So O1 acting on this state will give me a sum over lambda, O lambda, n lambda, times the same thing. Okay, that's what I just proved to you. Okay? So it is an operator that when it acts on any Fock state, it gives very simply a sum of contributions. For each lambda, I get the value of, if you like, the eigenvalue of this operator in the state lambda, multiplied by the number of particles that occupy the state. Very simple. So for example, if the operator describes energy, okay, and I have a spectrum defined by energy levels with the index lambda. So what will be the one-body operator describing the energy, the single particle energy? It is just the sum over energies of all the particles, right? But in this language, what are the so if I have some spectrum, okay, and I have one particle here, two particles. This is of course for bosons, right? And 7 here or 5, okay? So what will be the total energy? And each of these states have a different energy. Epsilon 1, epsilon 2, blah, blah, blah. So what will be the total energy? I have to sum over all the energy levels, count how many particles I have in each, and then, for example, the state 3 will contribute 2 times the. Okay, it's trivial. Okay, so this is it. So if I'm writing a one-body operator in the basis that it's diagonal in, okay, then this is how it looks. Let me now write the final result. Just copying it. Okay, and this is where, or if I like, let me write it more explicitly. Okay. This will be our expression. Where, what is this? Now I have to remind you that I chose a very particular basis. What is the basis? It's a basis of eigenstates of O lambda. Namely, it's a basis where the matrix elements of the single particle operator lambda prime lambda is O lambda times a delta. Okay? So it's a very particular basis. Okay? And in this basis, it's convenient to write the one-body operator because it's just a number times the number operator times the eigenvalue. But what if I have a one-body operator and I want to write it in a different basis? And in some cases, it will be necessary. Okay? What do I have to do? Exactly. Now I use the transformation. Why I'm doing it? Because I want to write something that is the most general. Okay? It's not biased towards solving something. It's just what is given, and then, if you like, you can diagonalize it to find a better basis. But let's do it. So to be more general, I'll make a change of basis. And this is what it will look like. So let's now define a basis eta, like we did before, which is we know know how to okay. So if we want to go from the basis lambda to the basis eta in which O is not diagonalized, we are going to get the following thing, and the way to see it is to use this transformation, or if you like, use resolution of the identity twice. So let me do it quickly. Sum over lambda, and now I'm using you know what, let me just write the final result. It's trivial algebra, so I don't want to spend time on it. It's going to look like this. Generally, I will have to sum over two indices. Let me call it eta and mu of eta O mu A eta dagger A mu. Okay? Let me just check that. Yeah, that's the expression. So here the indices mu and eta are different indices of some quantum number that is such that O is not it's not diagonal. So this may be different from 0 for different for any eta, for any index. And the way I've written it here, you can easily see that if it happens to be diagonal, I'm back to this, where here O lambda is just a matrix element. But this is the most general thing. Now, if lambda, if eta is not the same as mu, if they are not the same, what does this operator describe?
השמדה של חלקיק מתדירות ניו, ויצירה של חלקיק אחר בתדירות ניו.
I completely agree, except that you don't have to, it's not necessarily a frequency. I mean, okay, just translating to English. Okay. So what does this describe? It describes actually a process whereby you destroy a particle at quantum number nu and recreate it with a different quantum number. For example, if the eta and nu describe different values of momentum, you may have a process where a particle changes its momentum. It scatters from some impurity and it changes from k to k prime. Or if they are describing different lattice sites, such a process describes hopping from I to I plus 1. Okay? So, but it is a single body operator, and you see that it acts on only one particle in the form that it's it has only one annihilation and one creation, so it doesn't change the number of particles. Okay? What it does, it just maybe change the state of each term in the sum, maybe change the state of the particle, or preserve it and just count it. Okay, but it acts only on one particle. Okay. Now we can also define operators that have two creation operators or two annihilation. Such operators usually will not describe physical quantity that has a well-defined expectation boundary, right? But they can appear, they are legitimate operators. What will they describe? They describe a process whereby you destroy two particles or create two particles. Okay? Now we'll see such examples, that such things are related to something with physical meaning, but by themselves, they don't describe a physical quantity that that can be measured. Okay? Okay, just like A and A daggers themselves, by the way, cannot be measured. They don't have an expectation value. They only have matrix elements. Okay? Okay, very good. So now let's quickly go to two-body operators. And before I'm doing it systematically, can you make a guess of how it will look? Just a guess.
או פשוט יהיה לכל איזה, נהיה שני השמדה בהתחלה ליד ושני היצירה אחר כך ליד אחד ליד השני. משהו כזה, ובפני המצבים יש שני חלקיקים במקום שלנו.
That's right, okay. So I already can make a guess that if this is one body, as a two body will be some A dagger. If I have a three body, I'll have A dagger. Okay, but let's do it more systematically. And in particular, I want to describe an interaction. Okay, so two-body operators. So two-body operators indeed describe interaction between two particles. And these particles may start from a state where they're in different quantum numbers or the same quantum number, depending on what they are. But most generally, I want to start from something that I also know how to write in first quantization. Like this is what we did in the one-body case. We wrote the kinetic energy or potential energy. We can write the total energy. We can write them all also in first quantization. If we want to describe interaction, how shall we write it? And let's start from classical mechanics. How do you write interaction in general? So suppose I have, in real space, I have one particle at R1. I have another particle at R2. Okay, and there is some interaction acting between them, right? And the interaction is described by a function that most generally depends on two coordinates, not on one, right? In many cases, it will actually depend only on the distance, but this is a particular case. Let's be general. Now, this is what I wrote here is a potential energy between two particles located at positions R1 and R2. Now I don't have just two particles. I have many particles, and each two of them are coupled by this interaction. And I want to write an expression that accounts for all the interactions between all the particles. How will it look like? I have to write it, and now I'm writing it as an operator, which I call V, okay, just V. It's going to be an integral over R1, integral over all R2 of V of R1, R2, but I have to multiply it by something that knows about the probability to find a particle there, right? So what is it going to be? It's going to be the density. I'm writing it like this because okay, let me write this. I don't necessarily have to write it in this order, but it's convenient. Okay, so it's the I have to multiply the potential at each point. I have to multiply the potential by the density of particles at R1 and the density of particles at R2. Okay? And the integral over all positions will give me the total potential energy. Okay? You use it in electrostatics, for example. Now, why the factor of half? It's to avoid the double summation, so we'll keep track of it. Very good. Now I want, sorry, I put here a hat, but the way I've written it here, it's not an operator, it's classical mechanics. What do I do to turn it into a quantum? I have to put the hat, but then what here is an operator? So in fact, everything is an operator, but the potential is already written here in terms of the coordinate. It's represented as a function of space, but these are operators, okay? And we already wrote here a definition of this operator in terms of creation and annihilation operators, but these are for the continuum variable R. Okay? So this is what it is. All right? And then to write it explicitly in terms of the field operators, psi and psi dagger, I plug in this definition and I get psi dagger R2 V and psi dagger R1 psi R1. Okay? Now, I'm going to do the following thing. You agree with me that for, so now notice that I have to be careful about the order because these are operators. And if I'm exchanging any two operators, I may pick a minus sign if they're fermions or plus sign if they're bosons. But if I take this operator and move it here, it's okay. The sign will, in both cases, will not change. But I have to be a bit careful because by doing this, I may pick some trivial constant. So, so in other words, when I do this operation, there's no minus signs for that, that's for sure. But there may be something else because if R1 is exactly equal to R2, for example, then I can have some delta. I can have some constant. Okay? So I'm going to subtract this kind of constant. In other words, I'm going to write here the following expression for a general interaction where let me write okay, I'll rewrite it here. Sorry that I'm not very organized today. So I write it like this. Here is the integral. And then psi dagger R2, psi dagger R1, then psi R1, psi R2. Okay? This form of writing an interaction operator is called normal order. And the definition of normal order is that all the annihilation operators are on the right. Okay? Now, why do I want to write it like this? Because I want to assume that the expectation value of V in the vacuum, okay, so if you like, this could be a definition of it, this is 0. And you can immediately see that it does, right? If I apply it on the vacuum, if I apply this operator on the vacuum, I get 0 because I annihilate it. Okay? So, now this is not necessarily true. I can always define my operator such that it will have some vacuum expectation value, because as I said, the vacuum is not necessarily just empty. But if this is the case, I'm not interested in it because it's like a ground state. So I can subtract it, and after subtraction, I get something that has a 0 expectation value. So I always define my operators in such a way that I can write them in terms of a normal order form, and then I don't have to worry about it. Okay? Okay. Now, the final thing is, I will not show the algebra, but the way I've written it, I started from knowing that the interaction in classical mechanics is expressed in terms of products of densities times some potential. Okay? But maybe real space is not necessarily the convenient basis to work in. I want to switch to some other basis. What would be a convenient basis? Now it depends on the problem. For example, I want to choose a basis in which the single particle states are diagonal. Okay, the single particle Hamiltonian is the diagonal, and then and we'll see examples. Then we can maybe, if we want to do perturbation theory on V, it will be very useful. Okay. So I want to change basis, and changing basis is going from real space to some other set of quantum numbers. Okay? Now, if I do it, I'm going to write to get the most general expression for so where's I'm going to get the most general expression for the two-body operator, which is maybe let me just call it O2, because it's any two-body operator. It's 1/2, and then a sum over 4 indices. This will be the most general thing, and this, if you like, we can call it matrix element lambda lambda prime mu mu prime of the operator. Okay? This is the most general form. Now, what is it? If I want to express it explicitly, so lambda lambda prime O2 mu mu prime. If O2 is some kind of interaction like this, then it's going to be an integral over R1, integral over R2 of the corresponding wave functions, which is R2, phi star, oh, don't have space, sorry. Sorry. I put here. I'm just rewriting it here. It's an integral of R1, R2, and then I have all the wave functions lambda prime, R2, V of R1 and R2, of phi of mu of R2, phi mu prime of R1. And now these are not operators, they're functions. They're wave functions with these quantum numbers which are expressed in real space. And this is an integral that you can solve, right? In some cases you can solve it. But it's just a regular integral over the two variables R1 and R2. Whatever it is, if you solve it, you get a matrix element. Okay, just a number, a parameter of the expression, and the two-body operator is, again, it's a sum over all combinations. And now, what does this describe? Each of the terms in the sum. It has some weight, some value, and the operator that we have here describes a process where you destroy two particles at mu and mu prime and recreate them at lambda and lambda prime, or if you want to describe it as a diagram, it's like a collision. You have two incoming particles with a mu and mu prime. Then they collide by something that represents this matrix element and recreated as lambda and lambda prime. Okay? And since they are identical particles, all you know, this is all you need to know, that there are two, you destroyed. It's like, for example, if these are momentum states, describes a scattering process where you have to conserve momentum, right? Okay, so let us stop here, and at 6 o'clock you have a tutorial. Next week we'll continue with a full lecture. Now, if anybody has questions, I have to apologize because I really have to run. I have some family thing today. So please use my office hours or contact me if you have.
Thank you.
More questions. Okay.
In your first degree, you notated the quantum state by some quantum number lambda, and now because we want to operate in this class with a macrocanonical system with many particles, we'll change our state, what we call the Fock state, and we'll represent it as such. instead of just writing the quantum number, this can be energy or momentum or whatever, we separate every different number to a different section in the vector and state how many particles we have in this quantum number, right? Now, I'm gonna go over definitions real fast so we can go into the real examples. First of all, we can add a particle to a state using a creation operator. We usually notate it as A with a hat or some other letter and a dagger. If AI works on a state and I will be equal to square T and I or and I plus 1 right. With this definition, we can create a simpler, different way to write our Fock state equal to equation of I AI dagger times AI divided by sqrt and I power of 0. Well, 0 is our vacuum state. So basically, we can take all of our particles and remove them using a reversed creation operator. Basically, instead of using a creation operator on a mode, we can extract creation operation. This is like a general state that you can write. I'm going to write it right here for a second. I'm going to write some definitions here. Right. Now we can also make an annihilation operator, AI, which works following way.
So I think it's MI plus 1. No?
Yep. Yep, you're right.
And here it's N.
This one is still correct. There was only a mistake here. Right? Let's go to I, 0, and I minus 1. We can first thing that we can see that if we use the annihilation operator on our vacuum state, we'll have a 0 outside and everything will be 0 out. Right. So second thing, the next thing, we can separate our particles in quantum mechanics into two different types. One is bosons and one is fermion. The main difference between them, that fermion has a Pauli exclusion principle in them. You can have...
למה שמת שם קו בסוף הסוגריים המשולשות שם בצד שמאל בשורה האחרונה? לא, בסוגריים
where was it? Ah, yeah. The fermion is the Pauli exclusion principle, which means that only one particle can have can be in a certain state. We can have two particles, for example, in the same energy or have the same exact So this equation now changes to, this is for bosons. In fermion we can shorten it a little bit. I 0, where I 0 or 1. The last thing before we go to some examples and some questions.
Yes.
Yes. Is a definition of a commutator. When we talk in the boson terms, the creation annihilation operator, we have what we call a commutator, A J. Commutator is defined by the first operator times the second operator, so AI AJ dagger, minus the second operator times the first operator, J dagger AI. In general, AB equals AB minus BA. In fermion, we have the anti-commutator, which is equal to AI AJ dagger plus AJ dagger AI. Again, I'm just going to write the general expression. AB equals AB plus BA. Now, some definition on the commutator. Commutator of AI AJ without dagger is equal to AI dagger AJ dagger equals to 0. The commutator AI AJ dagger is equal to lambda IJ delta IJ. And the same goes for the anti-commutator. AI J equals AI dagger AJ dagger equals to 0. AI AJ dagger delta IJ. Right. Now let's use these tools to do a question. Let's assume that we have a starting Fock state which is equal to 2.
רק מה שרשמת שם משמאל זה רק לבוזוני, ומה שרשמת
זה בוזוני?
זה
פרמיון. This is our starting state, and we want to find out what's AI phi equals to using only the creation operator and the commutator. relationship. So, answer. First of all, if you want to use the creation operation in the commutator, we have to open up this Fock state to the second representation. So we have 2 times A1. So we have divided by square root of 2. And we have 1 time A3. Right? Multiplying by AI. Square root of 2. A3. 0. Now, use the commutation relation to switch around the AI A1 dagger. So we'll have yes, delta I1 AI divided by square root of 2 A3 0 plus AI dagger A1 dagger, sorry, AI A1 dagger 1 divided by square root of 2 A3 dagger. No.
You only have one dagger on the beginning.
Oh, this?
No, the first equation and with the side.
Right. Right. So here there should also be A1 dagger, A3 dagger. Okay. Now I'm going to switch the AI here. Plus I1 A1 dagger, A3 dagger 0. As a mistake, there shouldn't be an AI. Go slower. Plus 1 divided by square root of 2. A1 dagger, A1 dagger, AI, A3 dagger 0. So here those two are the same. So 2 times 1 divided by square root of 2 is square root of 2. A1 squared, A3 squared, 0, plus 1 divided by square root of 2, A1 dagger, delta lambda 1 3 I3, plus 1 divided by square root of 2, A1 dagger, A3 dagger, AI. In red. AI operating on the vacuum, it's by definition 0. And we only have these two parts left. Did I forget the lambda here? I1. We see we have two answers. One when I equals 3, one when I equals 1. We'll have when I equals 1, square root of 2, 1, 0, 1. When I equals 2, we get 2. We get 0, sorry. When I equals 3, we get 2, 0, 0. Just taking this and doing the operation.
אתה יכול שנסביר את המעבר השני שעשית שם, את המעבר השווה השני שעשית בשורה השנייה?
זה?
הראשונה, כאילו משהו.
This one?
כן.
Alright. Let me just write only the operators. A1 dagger, A1 dagger, A3 dagger.
Okay.
Alright. Now I want to switch those two. And I know that the commutator AI A1 dagger is equal to AI A1 dagger minus A1 dagger AI equals to delta lambda I1. So taking this to the other side, dagger equals to I1 plus dagger. Next example. Let's say we have a fermionic two-level system. The quantum numbers, lambda 1, lambda 2. And we know we only have one particle in it. We want to find matrix representation of A1 dagger. So in a fermionic state, we know with fermionic two-level system with only one equals 1, with only one particle, we know all the possible states: 0, 0, 0, 1, 1, 0, and 1, 1. All of the states are orthonormal to one another, so we can define them as the basis of a matrix. Basically, saying this one is E1, E2, E3, E4. So to find the representation of A dagger, all we need to do is A dagger and A1 dagger in position ij is equal to EI A1 dagger EJ. So applying A1 dagger to the right we'll create another particle, because Pauli exclusion principle, we know that E3 and E4 will automatically be 0 here. And operating the creation operation on the left side will act the same as an annihilation operation. So we can't put on the left side a 0, 1 or 0, 0, as an annihilation operation on 0 will be absolute 0. We're only left with two possibilities. now this is this operator is position 3, 1. So if we start our matrix, dagger equals to line 3, position 1, 0, row 1, and then row 4, column 2, column 2. Everything else will be 0. Right?
הסיבה ששלוש פאור מתאפסים מצד ימין זה בגלל לא בגלל עקרון האיסור של פאור, אלא בגלל פשוט שזה יעביר את זה לאפס.
זה בגלל העקרון האיסור של פאור, זה יהפוך לאפס. If I do a creation operation on, let's say, this vector, it will add a particle here to 1, 2.
Sir,
Yep.
can you please explain why are those only two possibilities?
Mm-hmm. One second. Well, let me just write one thing, maybe it will help. Equals to alright. So now we must have A1 dagger of EJ and then 0 and A1 EI even than 0. A1 the annihilation on the vector removes everything that starts with a 0. The creation on a vector removes everything that starts with a 1. And in the end, we need to have that, let's write it like this, EI, A1 dagger, EJ be equal to, what is this parenthesis here? EI, because of the autonormality of the basis. Using all these three together, those are the only two remaining possibilities. Right. So now let's do a real example. All right. Schwinger bosons. Let's write it down. We know that a quantum particle can have an angular momentum, which we define in the quantum as a spin. But the spin has two components. One is the total spin, yes, and one is the Z component. M. In general, we can write the quantum state of a particle, a quantum particle, S M, where M is bigger than minus, bigger or equal to minus S, or between minus S and S. Right. We also have the up operator as plus, which operates such some constant. I'll touch it right now. Just 1. This minus has the reduction operator here. 1. I want to take this system and translate it into bosons, into simple annihilation creation operation in the boson state, in the boson space. This is a single particle ellipse.
זה תרגיל או שזה ממש הסבר על חום?
תרגיל. דוגמה. So, I'll define 2 operators, and we'll see as the class go on, and your homework will prove why they're right. I'll define A dagger, B dagger, such as A dagger A equals, and A equals S minus M, so S plus M, and B dagger B equals NB S minus M. Right, before we go into the translation, let's do some painting, some drawing. If I'll take here my Z, my spin, like a spin vector, where at the top we have absolutely positive spin, in the bottom it's minus S, and as we go up, go S psi 1 minus S, S psi 2 minus S, and so on. You can clearly see this translate to the S plus operator. And going down this ladder, S is minus 1, S is minus 2, down. This will clearly be the S minus operator. Now, let's see what happened to the NA and NB, the number of bosons in A and B. When we are at the absolute at minus S spin, we have S plus minus S, so it's going to be 0. S minus minus S, so it's 2S. Going up 1. Going up 1. We'll have S plus 1 minus S, so it's 1. 2S minus 1, so on. Of course, I'm going to write at the top is exactly the opposite. So on and so on. You can very easily see that when we increase our Z component, our A number increased by 1, so we have to add a boson, A dagger, but we also lose a B boson. Exactly the other way around as well. This one, so when going down, we increase the B boson count and decrease the A boson count. now let's also try to sort of hand wave translate the general state into the A and B basis. So S and we know that the number of photons in the A basis will be S plus m, and the B basis will be S minus m. And then using the creation operator definition from before, this m will be equal to A W S plus m square root of S plus m power BW S plus m minus m S minus m power. Zero.
So, can you explain the first line? What do you mean that? Yeah, what is it?
Notice that when we first defined our operator, we said that the number of bosons in the A state would be equal to the overall spin plus the Z component, and the B would be overall spin minus the Z component.
Okay, so
And-
we are
and-
moving to a basis of NA and NB.
Yeah.
Okay.
This, let me just make it clear. This is the spin basis, boson basis.
רגע, אבל יש לי משהו שאני שואל. אם אתה תחבר אבל את NA ואת NB אתה תקבל שני S, לא תקבל S. אנחנו רוצים לקבל מקסימום S בכל הסיפור הזה.
Why?
כאילו, ההבדל שלך, SZ צריך להיות S, הוא לא יכול להיות מעבר ל-S. פה אתה תקבל שוב פשוט זה...
Why?
כי
No,
זה
it-
NA ועוד NB, לא?
No, this is just I don't know where you get this connection, this condition, but it's not the case.
אוקיי, אז רגע, אז איך אתה מקשר בין NB לבין ה-ITL הזה?
We'll see in a second. I always lose it. I don't even need it. All right. Question. Now it's the question part. 1. Find S plus, S minus. Anyone?
רוצים למצוא את הפרטורה לעבודה בהתאם למה שיש לנו ב-A ו-B.
No? Hmm?
אתה רוצה למצוא את הפרטורה לעבודה באמצעות האופרטור לעבודה של
Yeah.
B.
Anyone have any idea?
A plus B.
שניים. NA קודם B קודם.
If we go back into the handy graph that I drew earlier, we see that an S plus translates into an increase in our A and decrease in our B. So I'll just do that. A diagram. Here if we have some sort of, let's say, I don't know, exactly the opposite, S minus. Notice that the commutator of those two is 0 because they're not operating on the same mode, so the order of writing is not important. Right? 2. Find Z using A/B notations. Use S plus S minus equals to Z, the known relation. Spins every time. Can I move this?
תסביר איך ידעת את הקשר באלף.
באלף?
כי איך קשור ההבדל על 10Z לבין הקשר בין ה-A פלוס וה-B?
I just sketched it out. Let's just sketched it out here. So I know when we go up, we also go up in the table. So we have to add one boson in the A state and reduce one boson in the B state. Increasing your boson is dagger, decreasing is without a dagger. So this was just like intuition, I guess. Well, since the question already told us what to use, let's try to use that. S plus S minus equals A dagger B, B dagger A. Now, bless you. Now, there's a known relation in the commutator. If we have a commutator of 2 operators and 2 operators equal to AC and then a commutator of B and D plus A BC B plus C A D B plus A C D B. Right. Get applying this relation to our equation. Get B dagger A dagger BA plus A dagger B dagger A plus B dagger A B plus A dagger B dagger BA, right? Now again, because A and B are two different modes, two different location in our boson, two different quantum numbers. The commutator of those two are 0 by definition, so this one goes, this one goes. B dagger, you know it's 1. And if you turn this around, you see that the minus, it's like minusing the entire commutator, -1. So it would be equal to A dagger A plus B dagger B. Nope, not plus, minus. Equals means Z equal to 1/2 A dagger A minus B dagger B. Again, A dagger A and B dagger B we already defined as the quantum, the number of bosons. So it's 1/2 an A minus in B. And if we'll put in the numbers that we define up there, although it's not legal, you can't just remove operator willy-nilly, however you want, however you like. But let's just imagine that I remove that I take the numbers here, put them inside our SZ. See, then let's write it legally. Equals 1/2 S plus M minus S plus M equals M. Very good. that's good. See, this question here. Prove that Z S plus minus equals to plus minus S. All right, let's do it just with the S plus, and you can try to do it with the S minus yourself. Z plus equals one half e dagger L minus e dagger B, e dagger B. A minus B dagger B. Now again using this relation, f of E dagger AB. Minus A dagger B minus B dagger B A dagger B minus A dagger B minus B dagger A dagger B. Right, for the same reason as before, we can remove some of this commutator, whatever, this one, this one, this one, this. This one is equal to 1. Right here, B dagger B minus 1. Get 1/2 is 2 A dagger B, or just A dagger B, which is equal to S plus. Very good. Can anyone tell me what's the time? Oh, wow, we have a lot of time. All right. Now we'll talk about one-body operators.
מה נשאר את התור השמאלי בבקשה?
in your bachelor degree, you used to define an operator on one particle. That's at least what I remember that we only did. But in one particle, we check its momentum and so on. For example, if we have a particle, some k vector, we know that the momentum of this particle, h bar, vector. Okay. Right? But now we have a larger, now we have the Fock state, nk1, nk2, and so on. We want to define the momentum, for example here, the momentum operator for this interaction, for this Fock state, general Fock state. We'll call it capital P. And we'll see in a second that it will just be equal to sum over h bar k nk. But it makes sense, this answer, because each of those modes, each particle in each of these modes have a ki. There's a ki amount of momentum. There's n particles with ki momentum, and summing all the momentum up, just get the momentum of each state times the amount of particles. But let's prove it. Right. We know if we have a continuous space and not an easily diagonal space, we know that P R equal to minus I h bar theta. Sorry. You saw in class the general equation for an operator, for one body operator, was integration over space phi r diagonal p phi r. Now I want to take this unknown wave function and put it in the basis that we do understand, which is the momentum basis. So the general Fourier transform by R sine k of divided by 2 A vector R vector k. But we know that in quantum our momentum is quantized, so we can replace this phi k with just an annihilation operator, with an operator, so it will be ak. Putting the Fourier transform back into our equation, Now, the operator, the constant here, the constant here, all of those do not depend on R, so I can on the position, so you can take them out. Bar. Taking the gradient in our function here, give us a k tag. K tag. Available L cubed minus I k minus delta R. This integral is just a delta function, if anyone recognizes it. K tag. So it will be sum over k, h bar k, ak dagger k, sum k, h bar k, and k, as our intuition predicted. So, what we did is we took the general function in the normal space, which is a non-diagonalizable equation annihilation operator. We transformed it into a state that we can diagonalize with operators, and try to compute this equation. We don't have time for all my examples, so I have to choose. Let's do the spin example.
אתה בעצם מתכוון שיש לך הקטע של אחסון בקטע של האופרטור הזו, מבחינת כאילו שאתה לא מערבב פה בין קיים שונים, זה בעצם הנקודה שלך.
שמה?
אתה בעצם אומר פה שאתה לא מערבב בין קיים שונים, זה בעצם מה שאתה אומר.
Here?
כן, אמרת שאתה diagonalization.
No, this is just because it's two different sums.
כן, ואז כאילו אמרת שאתה diagonalization ממקום שלא יכולת למקום שכן יכולת.
Oh, because the phi r is a continuous function and we cannot represent it in a Fock state.
אז כאילו רצית להציג את זה בעצם בתצוגה שהיא אחסונית.
Yeah, in creation or destruction in the annihilation operation. Now, let's consider a system with n spin half particles, and the single interaction operator Si. This is the smallest, but it's not much difference between small and capital S. So, H bar by 2. And the Pauli matrix. The Pauli matrix 1, 4, 2, 0, 1, 1, 0, 2 equal 0, minus I 0, 3, 2, 1, 0, 0, minus 2. Now, to write the one-body operator for the spin, we take, for example, let's try to find the SZ. This is a capital S Z. We know by definition that we have to sum over some function times the one body operator. This is the general equation. Let's try an example with it. Let's take state will be in
So what is alpha and alpha prime?
it's the indices. Basically, we have some spin half system, and we every index here represent the number of correlates to a photon, a particle in a certain state. So you want to find all the new element of the matrix, all the matrix.
But the indices in the sum are yeah, but what do they represent? Like, is it not a particle?
Mm-hmm.
It's not a
Oh, notice
particle.
that this is it's basically represent if there is like where's the position of particle alpha tag and alpha.
The matrix?
Yeah.
Oh.
You see,
למה שמת שם אבל שני אינדקסים? למה שמת מתחת לסיגמה Z ו-A אלפא שני אינדקסים?
זה מטריצה.
yes, also we can like in the previous example when we opened the function into a sum of operators, each function here has a different sum. This is like
ואז פשוט הכפלת את שניהם. איך נראה A אלפא עוד פעם? איך נראה A עוד פעם?
like this. A is just the creation of an annihilation operator. Right. So you want to find how this new operator work in some states. For example, n up equals 1, and down equals 0. So as a one body operator 1, 0. 1 divided by 2. Yeah, time dagger mazen alpha. We see here alpha will be either the up position or the down position. We know that if we just do an annihilation operation on 0, it will be by definition 0. So alpha will be equal to 1 in this case. Now, from the definition of sigma z, we know that only one will not be equal to 0. So alpha times also has to be equal to 1. Again, exactly what we expect. Notice that this only has one particle. If we have another index, z equal to divided by 2, found our secondary index, tag alpha, tag, so for every different index, lambda will have a completely different SZ depending on our population. Absolute general case.
מה האינדקס השני שם של סיגמה Z? אלפא טאג, מה רשמת שם?
אלפא? here?
לא, למה אתה שומע? מה אתה?
1.
אחד, למה אחד? אוקיי.
The delta that comes from there. It's time for an actual example. Right, let's try something hard. Because I'm tired of doing some trivial examples just to show the principle. Let's take a free electron gas with interaction.
רגע, אני פה שאלה קצרה לפני שאני מתקדם. מה שאמרנו לפני כן, כשעשינו את הדוגמה של האינטגרל הרציף והכל, ורשמת את ה-P, בוא נעשה את זה D בשלישית R, ואז רשמת שני אופרטור יצירה שם, אופרטור הורדה שם. בואו אנחנו נסתכל להעביר את זה למקרה הבדיד והכל. אז רגע, איך זה בדיוק מסתדר למקרה הבדיד ובמקרה הרציף? איך בדיוק? איך זה?
לא בטוח שהביא את השאלה. אתה רוצה לבוא לאחר?
אחר, אני אביא.
Since we have two, since in free electron gas we basically simplify it to interaction between two particles each time, we need to modify a little bit our continuous equation that you saw earlier. I'm pretty sure you saw it in your class, in your lecture. Continues here. You saw this equation in class, right? Let's solve it with a specific condition, specific potential. R1 minus 2 plus 2 squared R1 minus 2 value. I changed R and R tag to R1 and R2 to be more noticeable. So, solving this equation is exactly the same as we did when we only had one integral and one set of functions. We will change it to the k space, to the momentum space, and we can have a quantized equation with creation annihilation operator. Now it's many. There's vectors everywhere, but I just don't write the symbol of a vector. We take this, put it in our potential. Sum 2. Basically, we have 4 sums, so it's going to take a while to write it. Finally, again, everything that doesn't depend on R, I'm going to take outside. Whew. Now, to simplify this equation, I'm going to change some variable. I'm going to call R equals to R1 minus R2. And the integral, I'm just going to write again the integral. The noise. Yeah? So. Quiet breeze. Alright. So, separating these two equations, taking everything that depends on R1 side, a second. R of minus I. Now, this is one delta. One, two, three, four.
Why do we have for?
1 second. Yep.
Why do we have 4 kinds of?
I won't get a break. Meaning here,
We have K1.
because we changed this, we did this equation, which leaves us with R2 equals to R1 minus R. Yeah. Right. So do I have a minus? Mistake in the minus.
No, but it was before.
Well,
The black we already had K1, K2.
here. Oh, yep.
Yeah, here and before also. We have K1, K2, K3.
Oh, why we have 4 different K? Oh, because we have I erased the original equation, but we have psi dagger, psi.
Yeah.
Each one of those is a different sum over K. So overall you have 4 sums. You have to have 4. Yeah, physics and math is annoying like that. It's something. Alright, so again, it's delta. Let's hope I won't slip on the cup. This delta gives us the relation K1 plus K2 equals K3 plus K4. And I'll define a new index, Q, which is equals to K2 minus K3. And if you plug this Q back in the equation up top, you also see that it's equal to K4 minus K1. So, almost there. Equal 1 divided by 2 L cubed sum over AK R minus Q. time, it's no time. A, K3 my plus Q. You can check me on this. Wish. K3, A, K4. Integrate over D cube R EI QR.
You say DQR.
Hmm?
DQR.
D cube.
Ah.
Now, this integral is just a Fourier transform. Wait a second, I just want to write it. This VEE Q equals squared squared. Oh, sorry. This will just be equal. I'm going to give you the result here. This is just a Fourier transform, a known Fourier transform. So overall, VEE equals squared 2LQ over K3, K4, Q. A. What was it? Q dagger. A dagger. Plus Q A K3 A K4. All right. After we did this entire long calculation with too many integrals, anyone has any?
כמו אתנה, אולי כי יש שני חלקיקים פוגעים, ואז הקולטים תמונות שמעבירים בין עצמם, משהו כזה. אורי?
Yeah, I know your name, but just like you did it.
מישהו קרא את הסיפור לפני.
Yeah. You cheated. It's not fair. You cheated. You cheated.
Nice.
Basically, we take. How dare you? Let's say we have two particles. One of them is has a K3 momentum, and one of them has a K4 momentum. This entire interaction basically shows that they meet and exchange some sort of energy Q between them. K4 gives some energy to K3. Of course, Q can be with a minus. It's too late.
The Q squared.
Hmm?
The Q squared from the.
I did. 1 second. Right. And then that's it. My life is over. It's time. All right. There's 1 divided by Q squared. It's a normalization factor that should have been there and I forgot. It came from the Fourier transform of our potential. So, yeah, so basically this, we saw, we started with the general two electron interaction in an electron gas, and we saw it. This basically described a transfer of momentum between the particles. In your homework, you'll explore this equation a little bit more. And I don't think we have time for the last example that I wanted to do, even though it's the coolest one. And we had to do a lot of work to get here. So you'll see it in your homework with a guide, maybe. That's it.
Thank you.
28 minutes.